This is going to be chapter 6.6, which is going to be reviewing trapezoids and kites, which is kind of a special case of quadrilaterals. So let's go and get to it. So far we've been looking at parallelograms, rectangles, rhombuses, and squares, which are all kind of their own little quadrilateral family, with parallelogram being kind of the parent shape. So just to recap here, a parallelogram is a quadrilateral where the opposite sides, where the opposite sides are both, let me make sure I get the right color here. There we go. So let's try this again. A parallelogram is a quadrilateral with opposite sides that are both congruent and parallel. Those are the main properties of a parallelogram. A rectangle is a quadrilateral, that it's a parallelogram, so it has opposite sides congruent and parallel, and it has 4 right angles. So again, it's a quadrilateral, it's a parallelogram with 4 right angles. A rhombus is a parallelogram, so again, opposite sides congruent and parallel, with 4 congruent sides. So it's with all sides congruent rather than just the opposite sides. And then a square is all 3 of these combined together. It's a parallelogram, rhombus, rectangle, all wrapped up into one. But there are 2 shapes, trapezoids and kites, which are not related to a parallelogram at all. They don't have any. They're related in that they're quadrilaterals. They're kind of like cousins rather than descendants. So let's go ahead and look at them. So a trapezoid does not have a pair of opposite and parallel sides and congruent sides. A trapezoid is a quadrilateral where there's exactly 1 pair of parallel sides, not 2, like in a parallelogram. A parallelogram has 2 pairs of parallel sides, opposite top and bottom and opposite left and right. A trapezoid only has 1. And the parallel sides are referred to as the base edges or the base sides of a trapezoid. The other sides are called the legs. And again, this is because it kind of uses terminology from a quadrilateral and a triangle because it's the bridge between them. So if you take a triangle and you kind of chop the top off or you chop its head off, then you get this, which is a trapezoid. You also get another triangle, but that's beside the point. This down here, this is the trapezoid piece we're looking at here, right? So a trapezoid is kind of a cross between a quadrilateral and a triangle. Because like I said, if you take a triangle and you cut the head off, then you end up with a trapezoid. So aside from the base and legs, so just as a reminder here, these 2 edges right here, this piece and this piece, those would be the bases, right? And then these 2 pieces right here and here, those would be the legs, okay? So besides the bases and the legs, there's another type of segment that comes up, which is called the mid-segment. So the mid-segment is the line that connects the 2 midpoints of the legs. So, or basically it's the line that cuts both of the legs in half. So if I have a trapezoid, and I say this is the midpoint of this one, so that cuts that in half, and this is the midpoint of this leg, so that cuts that in half. And if I connect them, this right here is the mid-segment. So mid-segment. Okay? It connects the middles of both legs. And so a mid-segment's length is always equal to half the sum of the bases. So if I want the length of this mid-segment, I would figure out how big this base is, how big this base is, and divide them by 2. And it's always parallel to both bases, right? So this middle line is parallel to both the top and the bottom because those are my bases in this case. So just a quick little algebra here. So if I want to find the length of this mid-segment, it's going to be half the sum, right? So I'm just going to take 18 plus 24 and divide it by 2. So 18 plus 24 divided by 2. Let me do my calculator just so I don't mess it up. So 18 plus 24 divided by 2, 21. So it'd be 21 units long. And I can also go backwards, right? So if I have the mid-segment and 9, and I want to figure out how big this top base is here, I can say, okay, well, x is going to be equal, sorry, let me reverse that. I started with my number that I don't want. I can say that 8, which is the mid-segment, so 8 is going to be equal to the sum of x and 9 divided by 2. So doing some basic algebra here, I'd multiply by 2 on both sides to get rid of the division, right? Whoops. Multiply by 2 on both sides. Come on. There we go. Ah. So I get 16 is equal to x plus 9, and then subtract 9, and you get 7 is equal to x. Right? And again, you can check your work. 7 plus 9 divided by 2 is indeed 8. So again, mid-segment math isn't that hard. You just have to note that, once again, it cuts both legs in half, right? So it cuts both legs in half, and it's always parallel to the 2 bases, and it's half the sum of the length of the 2 bases. Okay? It has a lot going on with just one little segment there. And then a special kind of trapezoid exists known as an isosceles trapezoid. isosceles trapezoids, which I probably misspelled there, but that's okay. So an isosceles trapezoid is basically an isosceles triangle with the head cut off. So this is a special kind of trapezoid where both legs are congruent to each other, and the base angles are congruent. So that means if I have a trapezoid, it's isosceles. It's kind of an ugly trapezoid, but we'll go with it. It's isosceles if this leg is congruent to that leg, and then this angle congruent to that angle. So that's what makes it an isosceles trapezoid. And again, it could also be on sides, so you can have something like this. And then, if this leg is congruent to this leg and this angle congruent to that angle, that's also an isosceles trapezoid. It's just on side. So, but again, that's just like an isosceles triangle. Same rules for an isosceles trapezoid. And there are three main theorems. One is the definition, right? If a trapezoid is an isosceles, then both legs are congruent. That's kind of the definition of an isosceles trapezoid. And then if one pair of base angles is congruent, then it's isosceles. So that means that, if I have this, if I know that these two angles are congruent, then I know that these two sides are congruent, and that the trapezoid is an isosceles trapezoid. So this is kind of the backwards version of what we said here. We said that if it's an isosceles trapezoid, then the base angles are congruent. Here I'm saying if the base angles are congruent, then it's an isosceles trapezoid. So just the reverse of what I said before. And then a trapezoid is isosceles if and only if the diagonals are congruent. So this one's a special little case. So that means if I have an isosceles trapezoid, or if I want to check here, if I know that this line here, if that line is congruent to this line, if these two diagonals are congruent, then I know that the trapezoid is isosceles. If they're not congruent, then it's not, right? So that's one way to check to see if a trapezoid is isosceles, is to see if its diagonals are congruent. The way you can see that this is not always the case is, if let's say you have a right trapezoid. A right trapezoid looks like this. So right trapezoid kind of looks like a boot, right? Where you have a right angle right here. And you can kind of see that this diagonal right here is going to be much longer than this diagonal right here, right? These two diagonals are definitely not equal, but in an isosceles trapezoid, they should be. So that's one way to check to see if it's an isosceles trapezoid, is if the diagonals are equal to each other. And then lastly, we have a kite. So a kite is a special kind of trapezoid, or a special kind of quadrilateral. It's a quadrilateral with no opposite sides congruent nor parallel, right? The opposite sides are not congruent, and the opposite sides are not parallel. Instead, it has two pairs of consecutive sides, that are congruent. So it looks like this. These two sides are consecutive, and they're congruent. And these two sides that are consecutive are congruent, right? So the opposites are not congruent. The consecutive sides are congruent. The sides that are next to each other are congruent, except for, again, these two right here. So this pair is congruent, and this pair is congruent, right? Not the opposites like all the other shapes. It's a special little case. And so we have two main theorems. So if it's a kite, then the diagonals are perpendicular. So it's kind of a carryover of a rhombus. So here's a kite. That means that the diagonals, so this diagonal here and this diagonal here, are going to be perpendicular to each other. I think I said congruent, which is my bad. These diagonals are going to be perpendicular to each other. They're going to make right angles just like a rhombus. Okay? They're not going to be congruent, but they are going to be perpendicular. And if the quadrilateral is a kite, then exactly one pair of opposite angles are congruent, and it's the angles that are not between the congruent sides. So let me draw. This one goes better with a drawing than an explanation. So if I have a kite like this, that means that this angle here is going to be congruent to this angle here. Because again, I'm assuming that these two sides are congruent and these two sides are congruent. So the pair of angles that's congruent to each other is the pair that's squished between the short and the long edge. So this angle is between a short piece and a long piece. This angle is between a short piece and a long piece. Therefore, they're going to be congruent. This angle on top and this angle on bottom are not necessarily congruent. In fact, they often won't be. Otherwise, it'd be something other than a kite. So it's always the angles that are between the short and the long pieces. Right? So let's find the missing value of the angles here. So I know that this is 128 and this is 72. Okay. And I know that, again, I have a short piece here and a long piece here. So that means that this angle right here is going to be congruent to this angle right here, which is also between a short piece and a long piece. Now, again, I don't know what these are, so we just label them both as x, right? So this will be x and this will be x. Because if they're the same, I can use the same variable for both of them. Now, again, I don't know what they're going to be, but I know that all four of these have to add up to 360, right? Because it's the quadrilateral. So I can use my 180 trick, right? 180 times 360. Nope, sorry. I don't know why I put 360 there. 180 times n minus 2. 0 times n minus 2. And so 180 times 4 minus 2, which is going to give you 360, right? And so that means that my setup is going to look like this. 128 plus 72 plus x is going to equal 360. It basically becomes a problem like we had in chapter 1 of this section here, where you're trying to find the interior angle sum. Same deal. You have two missing angles that you know the variables for. So add all the angles up, set it equal to your magic number, which in this case is 360, and then solve. So this is going to be, let's see here, that'd be 200 is equal, or sorry, 200 plus 2x, so x plus x is 2x, is equal to 360. Subtract 200, you get 2x is equal to 160. Divided by 2, you get x is equal to 80. So each of the angles that are missing are both 80 degrees long. So again, nothing too fancy, but you have to know the properties that, okay, these two angles are going to be congruent to each other, therefore they're both going to be x, and therefore I can solve using the interior angle sum stuff that I did in chapter 1 of this section. And last, let's do a proof here real quick. So, given that this is a kite, prove that IZT is congruent to EZT, the triangles. So we're going to do blah, blah, blah given. And we have to use our properties of a kite to figure this out. Now, if I want to prove that two triangles are congruent, then I have my 5 theorems, right? I have angle, 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 side, side, that sort of thing. Well, if this is a kite, that means the diagonals are going to be perpendicular to each other, right? So I know that this angle right here, IZT, and this angle right here, EZT, they're both going to be right angles because it's a kite. So I can say that angle IZT and angle EZT are right angles. Right angles. Why? Because diags, for diagonals, diags of kite are perpendicular. I'll use this symbol here, perpendicular. So since the diagonals of a kite are perpendicular, I know that these two angles are going to be right angles. And because I know they're right angles, I can say that IZT is congruent to EZT because of right angle theorem. Right angle theorem says that all right angles are the same, all are congruent. But I actually don't need that here. I'm actually going to do one of those special proofs here. So you can notice here that ZT is in both triangles, right? Which means that it's reflexive with itself. So I can say that ZT is congruent to ZT because it's reflexive. Again, it's reflexive with itself, it's congruent to itself, so I can use that. And now I can actually say that these triangles are congruent using that special case of HL. Remember, HL works if you have a right triangle. And here, whoops, ZT. And here I pretty clearly have a right triangle. Sorry, this is EZT. My writing got messed up there. So this right here, IZT and EZT, are both clearly right triangles because they're triangles with a right angle, so they have to be right triangles. And therefore, I have the hypotenuse is congruent because that's a given, and I have a leg is congruent because it's reflexive. So I can use HL because I have a right angle, I have hypotenuse is congruent, and I have a leg congruent. So this is going to be congruent by HL, and that is QED, right? That's done. So there's actually a few ways you could do this. You could do it using side, side, side as well if you're clever enough. You could do side angle side probably too if you went through it a little bit more. But I think the easiest way of doing this would simply be doing HL because you have to prove the least in that case. So, right, and I believe that's it for this one. Yeah. So I just had a bigger picture of this over here in case we're in class and I wanted to use a little bit of a bigger picture. But this one sufficed for this one. So that's it for this video. Again, trapezoids and kites are kind of their own special little case because they don't follow the same conventions that a parallelogram does, but they're not too terribly tricky, hopefully. Once again, if you still need help understanding some stuff here, let me know via email or come see me, and I'll be glad to help you out. Otherwise, hopefully this video helped you out, and have a good day.